Let us start now. In the last class, I have started the chapter on the module on torsion. What I have told you that any prismatic bar of certain length and certain cross section can be subjected to various type of loading. Maybe loading can be axial, loading can be normal to the axis, and loading can be a couple or torque or twist. If a couple or twisting force or twisting moments or turning moments is applied to a shaft over its surface, it will the shaft is subject to twist or rotate about its own longitudinal axis, and it will deform accordingly. And what is the force induced in the shaft was given by this equation. Which is known as torsional equation. This is the equation which is we have made it here. That is the torsional equation. It is the torsional equation which tells us the relation between a twisting or turning moment T and the shear force that's created and the radius of the particular section or particular ring where which the shear force is created, the angle of rotation which is induced by this torque, which is equal to theta, and the length of the particular shaft or particular prismatic bar, and the polar moment of inertia J, and the radius of gyration, that in the radius of modulus of rigidity G. This is the full relation known as torsional equation. That is now, with the help of this equation, we can calculate that torque induced or the maximum shear stress which can be induced in the shaft, provided you know the length and you know the diameter of the shaft. And now shaft can be of two types we have imagined. Shaft can be solid and shaft can be hollow. For the solid shaft, the shear force is from this torsion equation is equal to 16T divided by pi dq at the outer surface. For hollow shaft, this becomes 16T into T, which is divided by pi capital D to the power 4 minus small d to the power 4, where capital D is the outer diameter and small d is the inner diameter. Now, there are some more equations, some more definition which we have introduced, which is defined as torsional moment or resistance of or resisting torque. What is this? The maximum torque which can be carried by a given section of the shaft for a given maximum value of shear stress is defined as torsional moment of resistance or resisting torque. So what is clear? We can apply for a particular shaft of particular raw material and particular length and diameter. It can carry a maximum torque before it fades. Well, with the condition that we know that torsional equation is applicable only when the Hooke's law is applicable, means stress is proportional to strain, and stress is the constant bar is stressed well within the elastic limit of the bar. Elastic limit, by means of elastic limit, you know, the definition of elastic limit is the amount of load, amount of stress of whatever may be the type, maybe torsional, maybe tensile, maybe compressive, up to which the deformation induced in the constant shaft will go back to the original shape and size when this additional external load is removed. This is known as The elasticity of the shaft or the load up to which this phenomenon is possible is known as elastic limit. Now this torsional moment of resistance or the maximum torque a particular induced shaft, particular shaft can carry is defined as the torsional moment of resistance or resisting torque. Now, J divided by R is defined as torsional or polar sectional moments. It's as per definition J divided by R. So J is the polar moment of inertia and R is the radius of the shaft. The torsional torque per unit twist is known as torsional twist tensor. So per unit twist, say per radian twist, torque per radian twist. To make 1 radian twist, what will be the torque required is given as the torsional distance, that is given as J into G, K, that is equal to K, torsional stiffness, which is defined as T torsional divided by angle of twist, which is given as J into G divided by L. Means torque per unit angle of twist is equal to J into G divided by L. This is defined as torsional twist or torque per radian twist. Next, another factor GJ, this one is defined as the torsional rigidity of the shaft, similar to the flexural rigidity. So G into J is another thing, is the torsional rigidity of the shaft. So G into J is equal to T divided by theta di L. Thus, torsional rigidity also torque per unit angular twist. This is also per unit angular twist is there for the torque per unit angular twist. Now, the shaft set, now we know next we have to calculate what is the power transmission. Where the shaft is used, the shaft is the connection between a prime mover and a constant motor, and a prime mover or a constant motor to the engine or machinery which is driving. Now, by means of this shaft, we are supposed to transmit a power from the motor to say from the engine of the automobile to the rear wheel of the car, from a motor to the prime mover, and from any others from a motor to the lathe. It's a lathe like this. So this power transmitted is the work done per second. You know from the definition of power, that power is T, the torque multiplied by the radian angle of twist in radians, means amount of torque it is induced, this power, torque is doing against amount of what this torque is doing, torque of this force is doing is equal to the power. So that is T, and radian, you know, 2 into pi into n divided by 60, where n is the RPM or revolution per minute of the shaft. And so this power becomes 2 into pi into n into T divided by 60. A shaft may transmit power more than one section to different machines. So this shaft may be subject to different torques and different machines for different machine. In case the principal conservation of energy is always applied, the shaft is designed to basically limiting value of the stress. Now, we know the shaft is designed. We are supposed to design here the shaft, means we are supposed to design the dimension of the shaft which for a given amount of power transmission. Now, how will you do? We have to follow the limiting value of the stress and the angle of deformation. With these two parameters, the limiting value of the maximum allowable stress. Maximum allowable stress means the maximum stress a particular shaft can carry before it is completely deformed or damaged. Also, you can say that the maximum stress it can carry up to its elastic limit, and the maximum angular deformation it can sustain with this maximum value of stress. So we have gone through two more problems then. First problem, a solid shaft, what is given is solid shaft, what is the amount of power transmitted in the solid shaft is given, it is 100 kilowatt, and what is the RPM this shaft is rotating is given 150 RPM. So we have to determine the suitable diameter of the shaft, means we have to determine the dimension, proper dimension and the maximum dimension of the shaft. If the maximum torque it can transmit, it sits by 20% for each solution. Here's a new factor is given. Not only that, the torque which we are will calculate it for the max as a maximum, we have to increase this 20%. So in order to take into account all sort of external phenomena. Next, the shear stress is not given. Shear stress as a maximum limit, that is 60 MPa. Also, now we have to find out the maximum length of twist which is possible for a length of shaft 4 meters, and its radius of that radius of modulus of rigidity G is given as 80 GPa. So with these factors and power transmitted, the RPM with which this power is transmitted is given, that how much torque will be transmitted, torque will be increased for to take into account of all the external factors is given. The maximum permission shear stress is given, and the modulus of rigidity is given. With this, and the length of the shaft is also given. With these known parameters, we are supposed to calculate the maximum diameter of the maximum suitable diameter of the shaft, as well as maximum angle it can twist. How we have done it? How we have done this calculation? We use this formula. This formula, that's P is equal to 2 pi into 2 pi n into T divided by 60. Here, the 60P, we determine the torque with this formula. T is equal to 60 into P divided by 2 pi n, where P is given as 100 kilowatt, or it converted into 100 watt into 100 watt. It converted by multiplying 1000 to into watt, so many watts, and RPM is given as 150. So if we put this value together, we'll get the torque equal to, in terms of 3606 Newton per meter. Tau max, T max, the maximum torque which can happen, we know that maximum torque will be 20% more than this calculated torque or design torque. So it is, we have multiplied it by 1.2, we'll get the maximum allowable torque, which is 7639. Or then we have to go, we know the torque.
Sir, 1.2 के बारे में समझाइएगा। 1.2 के बारे में सर टाउ टॉर्क मैक्स में टॉर्क मैक्स एक बार फिर से समझा दीजिए सर।
No, torque max is what is given here. You see that ekhane the maximum torque transmitted exceeds by means of 20% in each revolution, which means key for due to certain other practical phenomena in the surroundings, the maximum torque is supposed to increase. So it is given how much it can increase. So you have to use that increase in terms of your revolution in order to know the right dimensions. Okay? It is given in your problem, so you have to follow it. But in some other problem, you find that nothing is given. So we may say that maximum torque, which is calculated with this formula, is usable here. But here it's not like this. Here is saying that maximum torque is increased by 20%. So I am multiplying it 100 plus 120% or 1.2 with to the calculated torque here. This calculated torque is from this formula is 6366, which we are multiplying by 1.2, means I am increasing it by 20%. It becomes 7639 Newton per meter. And we are reducing to millimeter. So I am multiplying it 10 to the power 6 Newton per millimeter. To 7.639 10 to the power 6 Newton per millimeter. Okay. Next, I am going to the shaft diameter. We know from this equation, tau 16T divided by pi d cube. It's the relation between the shear stress and as well as the applied bending, applied twisting moments and the diameter of the shaft. Here, the maximum allowable torque is given here as 60 MPa. So I put it here 60, and torque T, which I have calculated by increasing it by 20%, is 7.639 to the power 6 divided by pi d cube, but d cube is our shaft diameter, which is unknown to us. So after solving this problem, we are getting the diameter 86.6 millimeter to the power 4. Next, we are supposed to calculate what can be the maximum angular twist. This is the maximum diameter. So this is the maximum torque T, maximum allowable shear stress. So diameter we put, a length is given as for 40 meter, we have converted into millimeter. So what we are getting, G is known 80 GPa, we are converting to MPa, 18 to 1000, and multiplied by theta and divided by L. And tau is 60 divided by R, which is the diameter of the dot divided by 2. So maximum allowable angular twist becomes 3.97. So the maximum diameter will be 86.6 and maximum allowable diameter angular twist becomes 3.97. Next problem is, which we have discussed again. Here what he has said, this shaft is not solid like the earlier one, but it is a hollow. It is transmitting 20 kilowatt of power at 150 RPM. So power is given in terms of kilowatt and RPM is given in terms of, rotation is given in terms of 150 RPM. Now total angle of twist in a length of the 5 millimeter of the shaft is 3%. So this angle of twist which I have calculated earlier, 3.93, here it is 3 degree and the length is given as 5. So what is supposed to be the, calculate the inner and outer diameter of the shaft, and permissible shear stress is 60 again and G is again 80 GPa. So what is given written down here one by one, power is given 200 kilowatt, rotation RPM is given as 150, length is given 5 meter and allowable shear stress is 60 MPa and G 80 GPa. So at theta allowable is 3 dB. So what will be the angular twist, the torsional moment or torque, which is available from this equation, 60P together 2 pi n. 60P is equal to 200 kilowatt. We multiplied it by 1000 to make it watt, and pi is 2 pi, and we put n as equal to 180. So 10 into 6.10 Newton per meter is the torque. Or we can again convert it to Newton per millimeter, 10.61 to the power 6 Newton per millimeter. Next, the angle of twist theta is given as theta pi by 100 degree, 3 into pi by 100 degree, and so theta is given as 3 degree. We know we can convert theta into radian by multiplying it by pi by 180, so it becomes 0.524 max radius. That is the maximum angular twist available in terms of radian, and it was, which was 3 degree in terms of degree. So again, from the torsional equation T divided by J, G to theta by L, what will happen? We know the torque, we know the, we don't know polar moment of inertia because we don't know the diameter. But as per our earlier defined formula, we know this is pi into T, capital D to the power 4 minus small d to the power 4 divided by 32, which is equal to G, we know 80 GPa, we multiplied by 1000 to make it MPa, 80 into 10 to the 80,000, and theta is converted to radian, here 0.524, and L is given as 5 meter, so this is 5 into 1000, 5 to 1000. Thus, d to the power 4 minus d to the power 4 is 124 into 10 to the power 6. 124 10 to the power 6 millimeter, but still we don't know what is the maximum or what is the minimum there. So we have to use other formulas here. The relation between torque and the shear stress, that is T is equal to tau divided by pi by 16 to the power 4 minus small d to the power 4 divided by capital T. So you put the value of T, which is calculated here. Pi is given here. Pi by 16 is all is a numerical value, and we put others are a others are unknown to us, d to the power 4 minus small d to the power 4 by t. So d to the power 4 minus small d to the power 4 is equal to 900,605 capital T. And we know this d to the power 4 minus small d to the power 4 is 124 into 10 to the power 6. So we put them in this equation, this value in this equation. So 900,605 is equal to 124. It is wrongly written. Actually, it will be 124 to the power 6. Or here, capital D is equal to 143.2 millimeter. That is the outside diameter. And you put it in this equation. Capital D is equal to 143.4 multiplied to the power 4 minus small d to the power 4 is equal to 100. Actually, they are using this equation 124 into 10 to the power 6, or D is equal to 130.7 millimeter. Thus, we got both this small and capital T. Now, let us go through one new problem. Compare the weights of the weights of a equal length of solid and a hollow shaft to transmit a given torque, provided for the same maximum stress if the inner diameter of the shaft is 3/4 of the outside diameter. So we want to calculate, we want to know we want to compare the weight of two equal lengths. Compare the weight of two shafts, one is hollow and one is circular, but length is equal. But diameter outside, one is hollow, one is solid, and they are supposed to transport a same torque at same power. If there is one relation between the inner and outer diameter of the shaft is 3/4 of the outer diameter, 3/4 of the outer shaft. So what is given? Length is equal, solid and hollow shafted length is equal. They are transmitting same power. They are having the same maximum stress because they are made of the same material. The inner diameter of the hollow shaft is 3 into d divided by 4. Now let us compare the weight of the two shafts. What will you do? We have to know the diameters. So what is that? The torque transmitted and shear force and allowable shear force is same for both the diameter, both the shafts. For solid shaft, just a second. So a solid shaft T divided by capital T, that is equal to pi into d to the power 4 by 60. For hollow shaft, same relation is T divided by capital T and pi capital D to the power 4 minus small d to the power 4 divided by 16t. And you replace small d to the power 4 by 3 into t by 4. This relation will becomes pi d to the power 4 1 minus 81 by 256 divided by 16t. Or other further subtraction, it becomes 0.6836 multiplied by pi to the power 3 divided by 16 divided by 16. So what we have, this relation P torque transmitted the shear force is same for both the cases because we have the maximum shear stress and transmitting the same torque. So this relation we can safely equating them to thus it becomes pi into d to the power 4 into 0.68 pi to the power 4 16 by pi to the power 4, or capital D divided by small d is equal to the diameter, outside diameter of the hollow shaft divided by outside diameter of this base shaft, which is equal to 1.135. So ratio of the weight of the equal lengths, their length is equal. So area of the hollow shaft multiplied by weight will be area of the hollow shaft multiplied by length, which means it's like this. Area of shafts multiplied by length multiplied by specific cavity, specific weight. So this is length is same for both the shafts, specific weight is same because they are of the same material. So area of the shaft, hollow shaft divided by area of the solid shaft. Ratio of the weight of equal length, area of the solid shaft. So what we are doing, area of the hollow shaft becomes capital pi d to the power 4 d square minus pi small d square, where d is the outside diameter and small d is the lower diameter. And we know the difference between we know the relation between capital to small d square. So we put 3d by 4 by 3d divided by 4 as that as small d to the power 2 divided by the diameter of the solid shaft, which is the diameter of the outside diameter of the solid shaft divided by outside diameter of the solid shaft, because becomes 1 minus 1.6. And this we have this relation 1.135. This is the relation between capital OD of the hollow shaft divided by OD of the small shaft. So we put it here as multiplied by the same value and multiplied by 7.7 by 16. So ratio of their ratio of their weight is equal to 0.564. So what you see that the hollow solid shaft almost 1.5 times more heavier than the hollow shaft. That's why in order to set a considerable amount of material, we can use solid shaft, hollow shaft in case of solid shaft to have the same power and same for to substitute the same power and torque, and for the same length. That's another problem. The shaft transmit that a shaft transmit 280 kilowatt hour of power at 160 RPM. So what is given, what is the power is transmitting is known, and what is the RPM it is rotating is known, with which we can know what is the torque it is developing. So what from this relation, another thing what we are supposed to know, the diameter of the solid shaft to transmit the power, the inner and outer of the hollow shaft, if the ratio of inner and outer diameter is 2/3, and the percentage saving in the material on using a hollow shaft in case of a solid shaft. Allowable stress is given as 80 MPa, density or rho is given as density of specific or specific weight is given as 78 kilonewton per millimeter. Now, what is given? A solid shaft. What is given? The power transmitted RPM, the allowable stress. It should be tau, not T, but tau. Allowable stress 80 MPa and rho, that is the specific weight 78 kilonewton per kg. So what we are supposed to find out, diameter of the shaft, inner and outer of the hollow shaft, if the ratio of them is 2/3, means inner diameter is 2/3 that of the outer diameter. Percentage is saving in material of the shaft over solid shaft. What is the difference in weight of them? 8%. So we know this formula P 2 pi nt divided by T. We know that is the maximum power, transmitted power 280 kilowatt, and we know we know the RPM, that is 160 RPM, and T is becomes equal to 16.71 kilonewton per meter per minute, or 16.71 Newton per millimeter. For solid shaft, we know this from this relation. Transmitted torque divided by the shear stress is equal to pi to the power 3 divided by 16. And 16 into 71 to the power 6 divided by 80. 16 into 71 to the power 6 we have calculated, we put it here, and tau is the shear force, that is tau is the shear force 80. That is equal to pi to the power 3 divided by 60, which where D is unknown to us. So for the solid shaft, for this after calculation, you know, capital D says 102 millimeter. For hollow shaft, we have to do this equation. Capital T divided by tau, divided by is equal to pi into d to the power 4 minus 2 into d divided by 3 to the power 4 divided by 16t. Or after simplification, we know 16.71 to the power 6 divided by 80. 80 to the power 4, which is given here. Torque is given 16.71 to the power 6. We have calculated just allowable shear stress is given at 80 MPa, and which is equal to 65 pi to the power 3 divided by 81 into 60, or D is equal to 109.8 millimeters. So, and inner diameter will be 2/3 of the outer diameter, means inner diameter is 13.2 millimeter. What is the saving of the material? This is the pi/4 d square is the cross-sectional area of the solid shaft minus pi/4 capital D by 2 into d by 3 to the power 3 is the cross-section area of the hollow shaft divided by the area of the maximum shaft. We know because they are of same material. This is multiplied by the density of both the side, and they should cancel each other. Thus, we got the relation 1 minus 5d square by 9d square, and we know we have to put the value of d and capital D and small d here, and this relation becomes 0.356 or 35.6%. So by using, it is clear that using hollow shaft in case of solid shaft, we are saving 35.6% of material. Let us go through another one. Compare the resistance to torsion of a given shaft. The torsion of the hollow shaft to that of the solid shaft, if the inside diameter of the hollow shaft is compare the resistance to torsion of a hollow shaft to that of the solid shaft. If the inside diameter of the solid shaft is 2/3 of the external diameter and two shafts have the same material weight and of equal length. So what is given? Resistance to torsion. What is the maximum torque which can carry of a hollow shaft to that of the maximum torque it can carry by a solid shaft of the inside diameter is given of the inside of the hollow shaft 2/3 of the external diameter and two shafts of the same material. So relation between the internal and external diameter of the hollow shaft is given as which is equal to inner diameter is equal to 2/3 of the outer diameter. Another thing is they are of the same material, they are of the same weight, and they are of the same length. So you have to find out what is the resistance to torsion, or how much torque, how much resistance it can carry. You know, the resistance to torsion means is the maximum value of the shear stress for the maximum torque which can be carried out by the intersection of the shaft for a maximum value of shear stress, which is defined as torsional moment or resistance to torque. The maximum torque it can carry, which are supposed to calculate in both the cases. So, what is the maximum torque a solid shaft can carry, and what is the maximum torque is a hollow shaft can carry, and we have to compare them. And provided they have the same raw material, they have the same length, and they have the same weight. And the relation between the inner and outer is no given. Outer diameter of the hollow shaft is given. It is inner diameter is 2/3 that of the outer shaft. So let us have D is the diameter of the solid shaft, small d is the diameter of the solid shaft, and capital D is the diameter of the hollow shaft. So weight of the two shafts we are supposed to be same. So pi by 4 for the solid hollow shaft, pi by 4 into d square minus 3 into d divided by 3 whole square. As we know, the relation with the inner diameter of the hollow shaft is given as 2/3 of the outer diameter. And that is we are equating the cross-section area of the solid shaft, which is pi by 4 small d square. So the relation between capital D and small d, as we are established, means the diameter of the outside diameter of the hollow shaft and the outside diameter of the solid shaft is given as, relation between them is given as D is equal to 1.342 into T. Now, what is the resisting torque? We know the relation between that of a hollow shaft is T divided by capital T. Capital T means the turning moment, which is applied to the shear stress, the allowable shear stress, pi into D. Allowable shear stress is equal to pi into D to the power capital D to the power 4 minus 2 into D divided by 3 to the power 4 divided by 16D, or 16 pi by 16 in 65 by 81 D to the power 3, or this has become pi by 16 1.939 D to the power 3. That is the relation between the resisting torque and shearing, the ratio of the resisting torque and the shear stress of the hollow shaft. And same for the same way, the resisting torque and shear stress of a solid shaft is T into S divided by capital tau pi D to the power 2 by 16. Then ratio of the resistance to torsion, we know the shafts are of the same material, they are of same length, and they are of same weight. So this tau is same for both the shafts. So if we take the maximum stress are both same for both the same. So ratio of torsion will be for the hollow shaft and solid shaft, thus will become, if you take the ratio of these two side equations, it will become T into H by Ts equal to 1.939. That is our answer. Let us have another problem to finish this portion of the shaft. The 6 into 17. Let us have 10.6. a solid shaft transmitting 800 kilowatt of power at 210 RPM, 800 kilowatt at 210 RPM. Determine the actual working stress and the diameter of the shaft if this shaft twists 1 degree on a length of 80 diameters and length of 18. Diameter of the shear stress is not to exceed 15 MPa. And take G is at 81 MPa. So what is given here? It is a bit complicated. Let us discuss. The power transmitter is given and RPM is given. You know very well the transmitted torque we can calculate from the relation, but from the given relation. But what you're supposed to do, the actual working stress and the diameter of the shaft. If the shaft twist, there's another problem is given. For 1 degree of twist on a length of 80 a length of 18 diameters. What do you mean by this matter? Length of 18 diameter means length will be is equal to 18 into D. Length of 18 diameters. Length is equal to 18 times the diameter of the shaft. So length is also given in terms of diameter. And shear stress is not to exceed. This is also given as 50 MPa. And the radius of modulus of rigidity is given at G 81 GPa. Now, the given P is equal to 800 kilowatt and N is equal to 210 kilowatt RPM. So what is given here? Length of the shaft is 16G. Length is given as 18D, but we have discussed why. Tau is given as 15 MPa, and for 1 degree, theta is given as 1 degree, which is pi by 180. So P from the relation P is 100 kilowatt, and 100 kilowatt, which is can be converted into 800 into 10 to the power 6 Newton per millimeter per second. From the angle of twist, torque is T is given as T into G. We know from the theory of torsional equation, T is equal to J into G into 3 divided by L. What is given here? J pi to the power 4 by 32. We don't know the diameter. And G is given as 81 into 10 to the power into 1000 MPa. And L is given as 18D. And theta is given as pi 1 degree, that is pi by 100 degree. 1 into pi by 100 degree. So from this relation, torque is given as T is equal to 7.711 D to the power 4. And the maximum shear stress is given as 50. So maximum torque will be actually given from this relation 19.917 D to the power 4. So here the maximum shear stress limit will be, maximum torque limit will be 9.81, which is more than here, more than this torque. So we have two relations. One is the maximum shear stress and another is maximum angle of twist. And the torque transmitted by as per the maximum angle of twist is given as 7.711, and torque transmitted the maximum stress is given at 9.81. So we have to use this torque here to 7.11 because this is the minimum one, and we cannot twist it more than 1 degree. We can twist our shaft more than 1 degree. So thus, the process smaller matter of safe working, what we do, P is equal to T into omega. P is given as 800 to the power 6. Torque, we have put it here, that minimum one, that's 7.71. Omega is 2 into pi. RPM is also given here. RPM is 210, that is 2 into pi to 210 by 60. Thus, this equation dot D is equal to as 167.7 millimeter. Actual working stress, thus tau is equal to 16T divided by pi into D square. Here we put the value of this T, 6167.7 and to the power 3. That is 39.3 MPa. Thus, it is very clear that this is the maximum shear stress. We are using the maximum angle of twist in case of maximum shear stress, as it can, by following the maximum angle of twist, we are having less amount of torque, which it can transmit, and for following the maximum shear stress, we have higher amount of torque, which is not usable, because if you apply this amount of torque here, the angular twist will be more, which is not more than 1 dB, which is not allowable to us.